My second exemplar then involves a vehicle driving over a humpback bridge. Now, this brings some very important points to light. So let's look at this diagram and consider the van simply parked on top of the humpback bridge, and consider the forces acting on the van. Now, there would of course be the weight acting vertically downwards, and there would be the reaction. Now, of course, the reaction will be at the wheels, but let's imagine the reaction just here. Okay, so we have the reaction up, we have the weight down, and these two forces on the van are balanced because there is no acceleration in any direction in this scenario, because we started off thinking about the van being parked here, but no acceleration vertically. Now, those are, if we ignore air resistance and friction, those are the only two forces acting on the van. It doesn't matter whether the van is parked or driving over the bridge. Those are the only two forces acting. So when the van is driving over the bridge, because it's performing part of a circle, its direction is changing, which means its velocity is changing, which means it's accelerating, which means there must be a resultant force. Now, the only way there can be a resultant force towards the center of the circle, of course, is if either the weight gets bigger or that reaction gets smaller. Now, the weight depends on the mass and on gravity, which in turn depends on the planet. They're not changing. So the only way for there to be a resultant force towards the center of this circle is if the reaction gets smaller. Now, you know that the faster the van goes over the bridge, or the more humped the bridge is, the smaller the radius of the bridge, then the bigger that centripetal force will have to be. Because, of course, the rate of change of the velocity is greater if the van is going over the bridge faster, or if it is a steeper bridge, a smaller radius circle. So the centripetal force has to be greater to keep the van following the circle. And here's the important way of thinking about it. The centripetal force needs to be greater in order for the van to maintain the circle. Now, the maximum that centripetal force can be is the weight of the van. If the centripetal force required, because the van is traveling faster, for example, if the centripetal force required is greater than that which is available, the weight of the van will not follow the circle. The van will get air, as you might say. It will not follow the circle. It will leave the road. Think about that. So you have a maximum centripetal force available, which is the weight of the object, in this case the van. If the centripetal force required, because of the radius of the circle or the speed of the object, if that centripetal force required is greater than the force available, that circle will not be performed. So let's then look at the detail of this question. So figure 1 shows a parcel on the floor of a delivery van that is passing over a humpback bridge on a straight section of road. The radius of curvature of the path of the parcel is r, and the van is travelling at a constant speed v. The mass of the parcel is m. Draw arrows on figure 2 below to show the forces that act on the parcel as it passes over the highest point of the bridge. So you're going to have the reaction vertically up, and you're going to have the weight acting down, and I would show the reaction being shorter than the weight to show that there is a resultant force towards the centre of the circle. Those two lines need to be collinear, they need to be along the same line. I would draw my weight from the centre of the parcel. I would draw my reaction from the floor of the van, but I would show the reaction arrow being shorter than the weight arrow. Write down an equation that relates the contact force R between the parcel and the floor of the van to mvr and the gravitational field strength G. Well, I've already said that the centripetal force is the difference between the weight and the reaction. The maximum centripetal force is when the reaction falls to zero, and so it's mg minus r. You've got mg down, you've got r up, you can see that from your diagram. And so it is mg minus r equals mv squared over r. Now we want to make r the subject here. So we need to rearrange the equation. And we end up with r equals mg minus mv squared over r. Then it says calculate r if m equals 12 kilos, r equals 23 meters, and v equals 11. Well, sticking in your figures there, you'll end up with 55 or 54.6 newtons. Now, if we look at our data, I've lost it, sorry. We have 2 sig figs, 2 sig figs, 2 sig figs. It should be 2 sig figs. But we're not asked to do it to significant figures, so 54.6 is okay. But you should always be thinking about sig figs and thinking it should be to 2, it should be 55. So, explain what would happen to the magnitude of r if the van passed over the bridge at a higher speed. What would be the significance of any van speed greater than 15 meters per second? So, you know that in order for the van to go over the bridge and stay on the bridge, the centripetal force needs to increase, which means that the reaction must decrease, because that's the only way of making the force towards the center of the circle bigger. So there's our first point. Sorry. Our first point is that r decreases as v increases. Why? Well, because mg is unchanged, but mv squared over r, the centripetal force, must be larger. And if you extend that argument, r will fall to 0. And if you go back to your expression, r equals mg minus mv squared over r, you're going to say that mg equals mv squared over r. So v squared equals gr. So v squared equals 9.8 times r, which I think was 11. We can find that. Yes, no, sorry, r is 23. So if we do 9.8 times 23, and take the square root, we get v equal to 15.01 meters per second. So what we're saying is, at 15 meters per second, r falls to 0. Anything more than that, the centripetal force required to maintain that circle at that speed is not available. And so the van will try to follow a larger circle. Let's just say it will leave the road. So there it is. Hopefully that's been helpful to you.